Hi, good day everyone. My name is Queen Angela Barber and for today, I'm going to discuss about the linear independence and the Wronskian. We were going to talk about the linear independence of functions in the context of algebra, and then we were going to focus about the set of functions. In the code of linear independence, y1 and y2 are linearly independent on an interval if they are not scalar multiple of each other. Now in two dimensions and they're two different functions, the linear independence is a bit little simple. It is just like it's not a scalar multiple by the other. In that case, y1 was just like multiple by y2. So, for example number 1, sine x and cosine x are linearly independent because sine x is not just a number times cosine. And for example number 2, x squared and 2x squared are linearly dependent because it obviously x squared is just if you times 2, so you're going to get to 2x squared. So what are we going to talk here is the second order differential equation. And now the question here is, how do you make an analogy if you have three or more functions? What is the linear independence of the three or more functions? Let me take you to the GM method. So this is GM method. These are vectors now, not functions, but they play a similar rules. And you can ask now what it takes a three vectors to be a linearly independence. The idea is that I can think linear independence of those vectors between adding them together, possibly with the scalar factors. And the question is, can I add them up in a way that adapt to just zero? For example, consider this. All I've done is I rearrange the vectors and multiply them by the constant. For example, these vectors multiply to minus 1 and others. But the point here is these three vectors is a way that I can add them up with the stretching factors. So it equals to zeros. So these vectors, whom we call linearly dependent, do the so-called non-trivial way to add up to zero. So let's going to use this idea going back to our context of functions. y1 and the yn are linearly independent on an interval a1 y1 to an yn is equal to 0 implies a2 is equal to an is equal to 0. So I want to imagine that y1 down to y1 down to yn are functions. So these n functions, the claim is that they're literally linear independent. If the only way you could take a linear combination that adds up to 0, so an a1 y1 all the way up to an yn, the only linear combination that adds up to 0 is a trivial one. All the coefficients are 0. a1 is 0, all the way up to the an is 0. That is means to be linearly independent, only way to get to adding up 0 is in the trivial way. So, as an example, let's consider the following. E with the power of x, e with the power of negative x, and cosine hyperbolic of x. So the answer here is e with the power of x plus e negative x over 2. So what that means? For these functions, there is a way to add them up to get the answer 0. So how to solve to get the answer 0? Then 1/2 of e to the power of x plus 1/2 of e to the power of negative x minus 1 times cosine hyperbolic of x is equal to 0. So, this example is linearly dependent. For these examples, we have three different functions of linear independent to linear dependent. How would you show that the functions are linearly independent? For example, e with the power of x and e with the power of 2x and e with the power of 3x. Now we're going to actually develop new tools which we'll talk about in this video. But sometimes you can use soft ad hoc methods. Ad hoc means it doesn't work always. It's going to work in this sort of specialized case. So in ad hoc method, we have for the answer in e with the power of x, e with the power of negative 2x, and e with the power of 3x is equal to an e with the power of x plus 8 2n with the power of 2x plus a3 n with the power of 3x is equal to 0. And then a1 z plus a2 z with the power of 2 plus a3 z with the power of 3. We can use this formula or method if we know about polynomials. For this method, it's a bit hard, the ad hoc method, because it's only specialized a little problems. That's why we need more synthetic method. And then we're going to tackle the second about the Wronskian. So now let's talk about the Wronskian. So this is the Wronskian. Imagine I have three different functions. The Wronskian of those three functions is the determinant of the following matrix. The first column is all about y1, y prime 1, and y double prime 1. For the second, y2, y prime 2, and y double prime 2. And for the third, y3, y prime 3, and y double prime 3. We're doing the Wronskian in these dimensions, but we can imagine doing it in different functions. And what we're going to use in the moment is a connections between the concept of linear independence and the determinant of this Wronskian. So to motivate what connection might be, let's actually just do two functions and we're going to have y1 and y2 and imagine they are dependent.
So first, I'm going to say sorry because there's an issue that arise while I'm solving on board. So now I'm going to continue with writing on paper and discussing about the word scan. So for example, suppose y1 and y2 is equal to ay1 are linearly dependent. And the run scan of this is w times t is equal to y1, y prime 1 ay1 ay prime 1 is equal to y1 ay prime 1 minus ay1 times y prime 1 is equal to 0. So you get this answer from here. y1 times a prime 1 ay prime 1 minus ay1 times a prime 1 is equal to 0. So here's our theory. For nice functions y1 down to yn, they are linearly independent if and only if Wronskian is not equal to 0 at some point t. For another example, are e with the power of t and te with the power of t linearly independent? So let's solve using Wronskian. So let's plug in, and then et times t with the power of e with the power of t plus te with the power of t minus TET times ET is equal to E with the power of 2t is not equal to 0. Since it's never 0, these functions are linearly independent. Hope you learned something in this video, and I'm sorry again if I didn't finish the video because there's some reasons and issues that arises. Thank you very much for watching.